So chemistry's big idea is the atomic theory. It's the idea that all normal matter is made out of atoms. Where did that idea come from? If you take a block of iron and you cut it in half, each half has the same properties as the original. It's still made out of iron. And you take each of those pieces and you cut them in half. All of the pieces have the same properties as the original. They're still iron. But how long can you go on doing that? Can you go on forever? Chemistry and the atomic theory say no. There's a point where you have to stop. You come down to the point where you've cut down to a single atom particle of iron. And if you were to smash that particle into smaller pieces, you would no longer have iron. So there are different kinds of atoms, and a material that's made out of one kind of atom is an element. You can see all of the different elements that we know about right at the moment over here. We know about 118 of these elements. And on the periodic table, you can see that you're given the name of the element, you're given a symbol, and you're given also a unique identifier called the atomic number. And we'll see later what the atomic number is. It's the number of protons in the atom's nucleus for that particular element. But the point now is that every element has its own atomic number. It's a label, it's an identifier for that element. So here's element 2, helium, with a symbol He. Now case is important. The first letter is capitalized and the following letters aren't. So remember that when you're typing this into the homework later on and it asks you to do element symbols. Here's the symbol for copper. You'd expect that most of the symbols use the first two letters of the element name as the symbol, but CO is already taken by cobalt, so they use the Latin name for copper to do its symbol. The Latin name was cuprum, so they use a Cu for copper. Here's silver, it's argentum in Latin. Here's gold, it's aurum, Au is what they'll use. Sodium is natrium, Na. Potassium is kalium, which they'll use a K for. And there are a few others hiding around there that you can dig out. See if you can find 11 elements that have symbols that don't necessarily match up with their names all that well. Now atoms can bond together in tight little clusters to form molecules. Chemical bonds are really strong attractions between the atoms that pin them in place inside of a molecule. So here are different ways that oxygen atoms can pin themselves together. You can have a free oxygen, and that's called atomic oxygen. And it's a very dangerous form of oxygen. It instantly destroys any kind of organic material that it contacts. About 96% of the Earth's atmosphere at the altitude where satellites orbit is atomic oxygen. And early satellites came back with this kind of dusty, frosty appearance because the atomic oxygen ate the outer surfaces and ate up the organic materials in the coatings on the spacecraft. Eventually, NASA learned that they had to coat things like solar panels with silica, a thin layer of sand or glass, so that they could survive being in high Earth orbit. The second form of oxygen is O2. Now notice in this formula that we've got a subscript 2, and that means there's two oxygen atoms bound together inside this molecule. And we'll learn later that there's a double bond. There are two chemical bonds between the same two atoms in this particular form. This is the form of oxygen that you're breathing now. Now, here's a third form of oxygen. You've got 3 oxygen atoms with 1.5 bonds between them. And this is a more unstable form of oxygen. It's called ozone, O3. And it's very reactive, and it'll decompose into the O2 and the O pretty readily when ultraviolet light shines on it. In fact, it absorbs ultraviolet light very effectively for that reason. And you've probably heard of the ozone layer before. It protects the Earth's surface from powerful ultraviolet light that is coming from the sun. You'll smell ozone sometimes around high voltage equipment. It forms there. All three of these different forms of oxygens, of oxygen, the element oxygen, are called allotropes, is a fancy name. So when you have a substance that's made out of one kind of atom, no matter how it's arranged, you can say you have different allotropes of that element. Another example of allotropes would be carbon has graphite, where carbon atoms are arranged in six-sided rings, and diamond, where carbon atoms are arranged in little tetrahedrons inside. And they're both forms of the element carbon, but the atoms are arranged and bonded together in different ways.